Thanks so much.
Okay, so today we'll have Jiaxin Guan talking about a lower bound on the length of signatures based on group actions and generic isogenies. Take it away.
Okay. Thank you for the introduction. So my name is Jiaxin Guan. It's actually the second time I see you here. Good to be back. And today I'll be talking about our research work, a lower bound on the length of signatures based on group actions and generic isogenies. So this is going to work with Dan Bonnet and Mark Zandri, and this work is appearing at Eurocrypt this year. Cool. So let's take a look at our title. So a lower bound on the length of signatures based on group actions and generic isogeny. So like, why do we care about these things? So the title has two parts. Let's focus on the second part first. Why do we care about these group actions and generic isogenies? Okay. So here's a story. So I was in Canada last month for in February to renew my US visa, and there's this visa officer looked at my CV and asked me the question. So what is post-quantum cryptography? So and this the following is the story I told the visa officer. I say in cryptography we like to have our favorite friends Alice involved, and they do all sorts of interesting or maybe not so interesting protocols, and they do a sort of interaction. And in cryptography, we want to have certain security or privacy properties of these conversations. And the way we achieve these properties is we show a reduction proof of these properties to certain hardness assumptions for the adversaries. Right? So essentially, if an adversary comes over and the adversary has a computer, if the adversary wants to break the scheme, all the adversary needs to do is to break the certain hardness assumption. However, maybe in the future, the adversary has access to not an ordinary computer, not a classical computer, but a quantum computer. Now the question is, a lot of the hardness assumptions we have nowadays, for example, discrete log or factoring, will be broken, and therefore the security guarantees of the protocols will no longer be valid. So the question is, what specific hardness assumptions should we assume that are resistant against an adversary with access to a quantum computer? So this is exactly what post-quantum cryptography studies. And nowadays, most of the post-quantum cryptography constructions are from lattices. And for the efficiency reasons, they're from structured lattices in particular. So this is not what our talk is going to be about today. But as you know, our cryptographers, we are always like paranoid, and we don't want to put all of our eggs into a single basket. What if one day there's some attack on analysis on the LWE, and then there's like all of the schemes will be broken. So essentially, we want to sort of distribute our eggs among different baskets, even though some other basket might be small, it's still some other baskets. So we want some smaller basket, and indeed, there's such a basket called group action-based cryptography, which is another candidate for post-quantum cryptography. So that's about that. That was the story I explained to the visa officer, and the visa officer said, that sounds very important research going on here. We need to do some additional administrative processes. So I ended up stuck in Canada while they do that for another month. So yeah, so that was why post-quantum cryptography is important. And it seems that the visa officer was agree with that. So yeah, so now let's talk about specifically group action-based cryptography. The following I didn't explain to the officer because it's very hard. It's not accessible to the visa officer to understand. So first of all, cryptographic group actions was first formalized in 2006 by Kovignas, and there's also another formalization in 2021. So essentially, what are group actions has three components. First of all, there is a group G together with a set X, and we will imagine the group as acting on the set X and with this specific binary operation. So this binary operation is going to take a group element and a set element, and it's going to output another set element. Okay, so that is sort of a group acting on, this is the group G acting on the set X. And in here, we require some properties of the group for the group actions. First of all, there is a group identity E, such that the identity group action applied on any set element gives you back the same set element. Okay, so it's sort of like it's the same thing as you would have an element for a group. Secondly, we require compatibility, or sometimes referred to as composability, essentially saying that you can compose two group actions together. Say if I apply the group action H and then apply the group action G, now I can compose these actions together by applying a single group action G times H. So this is for all G, H, and X. And these are the only two properties that we need for the purpose of this paper. You can also, for example, require that the group action to be commutative. But in this paper, we don't assume that for the group action. All of our proofs go through even if the group actions are non-commutative. So the security guarantee or the hardness assumption that we have in this case is a sort of a discrete log version, but in the group action. Essentially, given a set element and the result of a group element acting on that set element, it's very hard to find a specific group element. In this case, we have G star X. You can think about it. As X to the G. Yes.
What's the distribution of X and G in this assumption?
These are just given from the sample from the group.
It's like uniformly random.
Yeah.
Okay.
Yes. Yeah, so here you're essentially getting a random set element X, and you are raising this star operator corresponds to the exponent. You're raising this set element to exponent G, and we say it's very hard to find the exponent that you raise it to. It's very hard to find G. Okay. So
what's the concrete instantiation of this?
the concrete instantiation, there's isogeny, a lot of isogeny-based cryptography. They instantiate group actions.
Are you going to go over it?
Yeah, I'm going to in the next slide. We're going to talk about isogeny-based cryptography. Yeah. So first of all, groups are pretty much broken with a quantum computer. Given Schnorr's algorithm, because you are able to find the order of the group. However, the reason here's to give you some reasoning of why it might be secure. Here, the idea is that in the group, when you're doing exponent, you're doing exponent on group elements, and there is very structured for the group elements because you can do group operations on these things where the exponent is on, right? But here you're acting on this set X, and there's no efficient corresponding thing as a group operation within this set. So given two set elements, how are you able to combine them and get a new set element? It's simply here. So this is the reason why Schnorr's algorithm does not work against group actions. And in fact, it has been studied what are some possible ways to attack a group action, and the best attacks we have are still sub-exponential. Is it possible that there might be a better, more efficient attack? It's possible, but this is so far the best results. It's still sub-exponential.
When we use a sub-exponential, is that attack generic for any group X?
Yeah.
Any group N?
Yes, correct. Okay. So now the question is, how are we gonna instantiate such a group action? It turns out the very popular way to instantiate group actions is from isogenies. And isogeny-based cryptography studies exactly that. So what are isogenies? Well, this is the one sentence explanation I'm going to give on isogenies. We won't dig into that today because our proof only uses the fact that these isogenies are modeled as group actions. But roughly speaking, an isogeny is a group morphism between two elliptic curves. So it's sort of like how a elliptic curve morphism related to second elliptic. Okay, so that's sort of what an isogeny is. And the paper by Koviknas and this RS paper, they show that group actions you can actually be derived from isogeny graphs of elliptic curves. So you're building this isogeny graph, and where each node is a elliptic curve, and the edges correspond to the isogenies. And it turns out that you can derive group actions from these isogeny graphs. And following that, remember we have this sub-exponential attack on the previous page. So to circumvent these sub-exponential attacks, actually people start looking at supersingular isogeny graph, which is a specific type of isogenies. And it turns out that this supersingular isogeny graph, it has less structure than the normal, than ordinary isogeny graphs. and therefore it has less structure, and therefore the previous page, the sub-exponential attacks do not apply there. So you will be it will be more inefficient to perform the attack there. And however, this is if you follow any recent crypto developments. Last summer, there has been a lot of attacks on the key exchange protocol based on SIDE, which stands for super singular isogeny deviating. Actually, these 3 papers are appearing at Eurocrypt this year, and I think they're the best papers for this Eurocrypt. However, something to notice here is that these are based on a very specific hardness assumption, this SIDE assumption, and they are building key exchange protocols. So first and foremost, SIDE itself is not a group action because they're using this isogeny, they're taking out structure. It's no longer a group action, so it doesn't affect our bound today. And second, this attack does not seem to affect other isogeny-based protocols. So even though SIDE is broken, there are also there are still a lot of other isogeny-based cryptography candidates. That's why we think studying this problem is still worth studying. In fact, we think about it as we want to understand isogeny more, so that we should encourage more people to look at these signatures and exchange schemes. Yeah, so some other examples are C-sign, which relies on the commutative version of the SIDE, version of the SIDE assumption, C-side, which they call. And the attack on SIDE does not extend to C-side because it has additional commutative properties of the isogeny graph. And there's also C-fish, which is also based on the C-side assumption. And the fish here is for this is for compact super singular isogeny Jiaxin. They have put everything there is C related. And there's also ski-sign. So notice that ski-sign is also based on isogenies, but it has this another quaternion assumption, and which makes it not a group action. But ski-sign is another candidate for isogeny-based problems.
How do these signing or signature scheme, what's their concrete performance comparing to, for example, the schemes from Lattice?
Yeah, that's exactly on the following pages. Yeah. Okay. So yeah. So again, back to titles, we sort of have an insight of why we want to study group actions and isogeny-based cryptography. The idea is that we want to get more candidates that are supposedly post-quantum secure. Okay. And in this talk today, and in this paper, we specifically deal with a lower bound on the length of signatures. And the motivation is pretty straightforward. We want to get short post-quantum signatures. Okay. So if we only want classical security, it turns out that signatures can be really short. So if we use the Schnorr signature scheme, if we only want a classical 128-bit signature, all we need, the size for the public key together with the signature only needs to be 96 bytes, which is really compact. However, if we consider the other post-quantum signature schemes, for example, the lithium, the public key size plus the signature size is going to be 4,000 bytes. Okay, so that's a huge difference there. And for Falcon 512, it's only it's also like 1,500 bytes. And for either variant of the Ringo signature scheme, it's 50 kilobytes. So you can see there is a huge gap between here. And notice that the lithium, Falcon 512, and the Ringo, these are the finalists for NIST. NIST is like the call for post-quantum signatures. Okay, and we can see that they all perform not nearly on the same level of magnitude as a classical Schnorr signature. So of course, there's also ski-sign, which is a isogeny, which is based on isogenies and the quaternion assumption. It's very compact. It's 268. It's very compact. However, it is not directly from group actions. In fact, it cannot be categorized as a group action-based signature. So this was efficient, but it's still a bit longer than the Schnorr signature. So our question is there any signature schemes that are sort of like Schnorr-like signature schemes that are post-quantum secure, and those have short public key plus signatures?
I actually wonder, was there like proof or their signature generation time and what their
The time efficiency?
yeah.
Yeah, I'm not sure about that, because because we're studying mostly about the signatures,
I think-
about the length, yeah.
For the isogenies one, it's very slow. It's like,
So they need to wait
1
on the
second per
elliptic curve first, yes.
Yeah.
Also, they have this like, for C sign and C sign, they need this trusted setup place in the front, so that also adds on additional overhead.
Question, is there any like hash-based signature here?
I mean, C sign is very much, sorry, wait, C sign, I think that's not what it was. I think it was,
like Spring or XMSS.
Rainbow is a multivariate.
Yeah,
What is Belkan effect?
I think these are lattice based.
That is based.
I could be wrong,
no, it's like.
I think these are lattice based. Yeah, I mean, there's no direct hash based on here, I'm showing here, but I think it was ski sign is sort of more like a hash function. No, not ski sign, sorry. The site that's broken, that's more like the underlying mechanism is more like a hash based. Yeah. So yeah, actually there is a sort of C sign is very similar to Schnorr signature in the post-quantum setting. However, its size is 3 kilobytes. It's still a big size. And in fact, what we show that in this paper is that for post-quantum signatures that are based on group actions, there is a lower bound of lambda squared over log lambda, and this actually matches the C sign's parameter size. So in other words, the C sign signatures are of type 3 kilobytes. It's not a surprise to us. It's the best they can do. And we actually show that this lower bound matches the current upper bound in the degree.
So in your paper, do you have a concrete constant factor here? In big omega.
Yes.
Okay.
So what is the result statement, I guess, and what is the precise statement?
Precise statement, the actual theorem statement, we'll see in a few slides, yes.
Okay.
Yeah. So yeah, and I'll quickly go over our results, what our result means. And so essentially what we want to show is a lower bound for group action based signatures. However, here is a very tricky thing for us. So essentially we want to work in one of the generic group models. I don't know if you are familiar with that, but there are two options. First of all, there's Morris generic group model, and there is the other Schup's generic group model. What the difference is in Schup's generic model, you think about the way we access a group element is you get a handle to the group element, which is a sufficiently long string, which is a sufficiently long bit string that essentially you can do other computations on. So you're sort of given a random label of the group element, and you can do whatever computations on, and that label has sufficient mean entropy. You can also build crypto upon computations based on that specific label. However, for Morris model, you are given handles to specific group elements. You can think about a group elements handle is just 1, 2, 3, 4, 5. In that order, there's absolutely no entropy in these group element handles, and therefore you don't you can't do any meaningful computation on these handles given out to the users. So that is a fundamental difference there. And what they imply is that signatures are actually impossible in Morris model. This was shown by Dutling et al. In 2021. And yeah, the basic reasoning, essentially what they show is that you're able, after the adversary gathers sufficient number of signatures, the adversary can do linear algebra to come up with a new signature for a new message, whatever signature scheme you have. Okay, so signatures are impossible in there. And for the Schup's model, it is shown that the Schup's generic group model actually implies random oracles by Zendry and Zhang in 2021. So what does that mean there is that if we want to prove a lower bound for signatures in the Schup's generic group model, we're essentially proving a lower bound for signatures based on random oracles, which is a long open question that has been around for a very long time, which is totally very hard to do. Okay, so in Schup's model, we have to solve this open problem, and in Morris model, signatures are impossible. So if we prove a lower bound for signatures in the Morris model, that seems like meaningless, right? Because you can't even construct a lower bound there. Yeah.
Oh, So did you say that it's a open problem to construct signatures from just?
Not constructing, just the lower bounding signatures.
Oh, I
It is
see.
lower bound signatures from Van one.
I see, okay,
Yeah, it's constructing is not.
yes, okay.
Yeah. So lower bounding is very hard in Schnorr's model, and constructing is impossible in Morris model. Then if you can't construct, what's the meaning of giving a lower bound, right? So our observation is that while signatures are impossible in Morris model, actually ID protocols are possible in the Morris model. It's possible to have identification protocols, but not signatures. And in fact, what we actually proved is a lower bound for group action-based ID protocols under the Morris generic model. And we show the lower bound of lambda squared over log lambda. And we make the observation that all the existing group action-based signatures are based on group action ID protocols. They essentially just apply the Fisher-Shamir transformation to, essentially what they do is they construct a ID protocol and they apply Fisher-Shamir to get the signature protocol. So this captures all the existing group action-based signatures. Okay. And the bound therefore applies there. So the Fisher-Shamir transformation, essentially you can take an ID protocol and transfer it to a signature scheme, and with zero overhead. It doesn't add anything to the public key size or the signature size, and the lower bound also treats.
So in your proof, do you use the GGM or do you use like a generic group action model?
We use the generic group action.
Okay, but it still like implies random oracle if you use Shoup's sort of.
Yeah, this is very simple.
Okay.
So why does it imply random oracle? I don't understand it.
I personally, I personally kind of yeah, I don't know.
Like
Yes.
the
I'll put the institution rely on it. It's this implies random oracle is by this separate paper of why Shoup's model implies random.
Seems like maybe it would have something to do with the randomness in the handles.
Yeah, randomness in the handles. Essentially, they show that this like group oracle, you can use it as a random oracle. That's essentially what they show. But how did they show it? I'm not sure.
So your work is actually a lower bound for ID-based.
ID-based protocols. Yeah,
Is it possible to have a signature?
it's possible. As long as you, there's a slide towards the end of the talk that explains how to overcome this, how to circumvent this lower bound. There are several ways. First of all is to construct a post-quantum, construct a group action-based signature, which is not based on ID protocols. The other way is to make non-generic use of the group action. So in other words, you're deviating from Morris generic group model. And therefore, like our bound, because our bound is proven within the model. So if you're deviating from the model, then our low bound wouldn't apply. And the third is to introduce other harnesses. So those are three possible ways to circumvent our lower bound. But so far as we know, all the existing constructions are obtained by transforming an ID protocol. Not necessarily from Fisher-Shamir. There's also a transformation by Wunju, but it's still like the lower bound still transfers there. Okay. So yeah, so we'll take a look at so how exactly do we make this bound on ID protocols, and what exactly is an ID protocol with a group action oracle? So we'll take a look at what the object we're studying is. So the ID protocol is essentially very similar to a signature protocol, except that there is no message for you to sign. So in other words, there's two parties. There's a party called the prover, who has the public key and the secret key obtained through some a priori key gen process, and the verifier has only the public key. And both parties, they have access to this group action oracle, which they can query about group actions. Okay, and they're gonna go through whatever sort of communication between them, and at the end, the verifier is going to output a single bit, either 1 or 0, essentially telling us if the verifier is convinced that a party it's interacting with has hold of the secret key. Okay, so if you have the secret key, you should be able to convince the verifier that you have the secret key. So that is the completeness requirement of the protocol. And the soundness says that for an adversary, if an adversary comes over and eavesdrops on a whole bunch of previous transcripts, so they say the adversary has T transcript of an honest prover interacting with an honest verifier, and Eve also has a polynomial number of access to the group action oracle, then Eve interacting with the same honest verifier should not be able to get the Eve wins the game if the verifier outputs 1, where the verifier is convinced that the Eve actually has the secret key, whereas Eve actually does not. Okay. Does this make sense? It's sort of like forging signature kind of. Okay. Yeah. So we'll take a look at a very simple Schnorr ID protocol and see how it performs. What are the sizes there and how it performs in the group action setting. So here's an adaptation of a Schnorr ID protocol for group actions. So to sample the private key and secret key, we will sample 2 set elements such that you know the discrete log between them. So x0 and x1. And G is the discrete log between x0 and x1. Okay, so the private key is going to be the discrete log, and the public key is going to be the set elements. Okay, and then to convince and then to prove that the prover has knowledge of the secret key, which is this discrete log. What it will do is to sample a new group element, sample a uniform group element H, and then compute essentially x1 raised to the H star x1, and that is another set element, and that set element is sent over to the verifier, and the verifier then is going to send over a random bit B, and the prover is going to send over this group element R equals H G to the B minus 1. Okay. And then the verifier is just gonna output, is gonna just do this check, see if A is equal to R star X sub B, and output whatever output that is. And just take a quick look at why this is correct. So what is R times XB? Well, if B is equal to 0, then essentially it's R times x0. X0 is G times x1. It's essentially G to the x1 x is G to the 1 minus B times star x1. And if B is equal to 1, then it's just x1 itself. It's G to the 0 star x1. So and R itself is H times G to the B minus 1. Okay, and then we compose these together. This should be just H star x1, and it should be equal to A. So take a minute to convince yourself that this is true.
Yeah, could you say again which one is secret key, which one is public?
The secret key are the secret key is G, and the public key is x0, x1. Okay. G is kept private, and x0 and x1 are the public. So everything in orange are set elements, and everything in green are group elements.
Yes, that's a little bit versatile. That's kind of cool.
Oh, yeah. Okay. The coloring. Okay, there's more coloring on the next couple of slides. I just hope those will work. But yeah, but you should be able to check. Yeah, this the correctness follows, and everyone convinced that this is correct. Okay. Now, yeah, briefly we can argue about the soundness. Well, for soundness, essentially an adversary need to be able to open to either need to be able to answer to both B equals 0 and B equals to 1. Right. So what does the adversary need to send when B equals to 0? That is H G to the minus 1, right? And if B is equal to 1, then the adversary needs to send H G to the 0. Right? If you divide these two values together, then you get G, which is the discrete log between x0 and x1. These two public key elements. In other words, if an adversary can produce can convince the verifier into believing that it has the secret key, then it essentially breaks the discrete log assumption of the group action. Okay. So notice that here the soundness error is exactly a half, because there is a trivial attack that the adversary can do is to guess the bit B ahead of time and sample everything according to the guess bit B. So if the adversary gets the bit B correctly, then the adversary wins the game, and then with the exact probability it has. So we want this to be, so essentially we want a soundness error to be, say, 2 to the negative lambda. What we do is we will repeat the whole protocol lambda times. Okay? So if we repeat the protocol lambda times, now let's think about what's our public key size and what's our signature size. So the public key size, public key consists of 2 set elements. Each of them are lambda bits. So the public key size is 2 lambda, where lambda is a security parameter. And the public key, well, we're repeating the whole process lambda times, and each time we're sending over a single set element, and that set element is lambda bits. So it's lambda squared for the signature size. So the public key plus signature is 2 lambda plus lambda squared, which is not tight. Okay, because our bound shows lambda squared over log lambda. This is not a this construction is not tight under the lower bound. Okay. Next, we're going to show how we can optimize this ID protocol to be actually tight under our lower bound. So the observation is that back then, here you're essentially, I have 2 secret, I have x0 and x1. Essentially, I need to guess the bit B for the challenger, for the verifier. Now, essentially, we just extend it to more bits, or like you guess an index. So the idea is that now instead of having a key of these like public key set elements, and we have construct them in a similar way that xi is equal to gi times xi. Okay, so like you have secret discrete logs of publicly available set elements. Okay, here notice that g1 is just the identity. Okay, so construction is very straightforward. Very similar to previous the one that we saw before. Well, you sample a random group element, compute the corresponding set element, and then you send over the set element A. And now instead of producing a single challenge bit B, you would produce a random index C. And the prover now needs to compute this instead of H times G to the B minus 1, now it's H to the G sub C to the minus 1. And then we check the similar thing. Okay. So the correctness still follows from pretty much from the previous Schnorr ID protocol. Here we're just extending it to having multiple set elements in the key. Okay. So now think about what is this for soundness? So previously the adversary needs to only guess a single bit correctly, which happens with probably a half. But here the adversary needs to guess the index correctly in order to carry out the attack, which happens with only probably 1 over p. Okay, so we boost the soundness from a half to 1 over p, but the public key size grows from 2 lambda to p lambda. You now have p set elements in the public key instead of 2 set elements there. Okay. Notice that in order to boost this soundness 1 over p to a desired small negligible soundness error, we need to run the protocol repeat n times. Okay, so let's say here we repeat it n times. Now think about what is the soundness error here. So each step, the adversary is able to guess the index correctly with probability p, and with 1 over p, and then you need to repeat n times. The adversary needs to succeed for n consecutive trials. So it's just the soundness error is just p to the negative n. Okay, that makes sense? And what are we trying to bound? We want to bound the size of the signature, which is like the size of signature plus the public key size, and that's essentially p plus n. P is the number of set elements in the public key, which corresponds to the length of the public key, and n is the number of times you repeat the protocol, and each time you send a set element, so n is the size of the signature. Okay, so we want to bound this. So we just set n equal to p equals to lambda over log lambda, and you should be able to check that. If we set these to be n and p, then the soundness error is actually 2 to the negative lambda. Okay. And in this way, the public key size and the signature key size added together is 2 times lambda squared over lambda. Okay.
So before was lambda squared,
Before was lambda squared. Yes,
so
correct.
now we have log lambda.
Correct. Yes. However, notice that yeah, the bound doesn't really apply to the simple Schnorr setting. However, this property that S is equal to P to the negative n actually applies to the previous setting. Right? In the previous setting, what is P? P is the number of set elements. We have P equal to 2. And we repeat the protocol n times. So this property that S is equal to P to the negative n holds nevertheless for the previous simple protocol as well. And this is essentially the idea that we want to capture in our actual proof. Okay. So now we move on to our main actual theorem statement. This is so if we have a public point ID protocol, here that we deal with public point because the reason is that later on, because eventually we're trying to get a bound for signature scheme. And to do signature schemes, you do the Jiaxin transformation, which requires protocol to be public point anyway. So we apply the protocol to be public point, and we essentially show that this is the result that we have. C is the completeness, and P is the number of set elements in the public key, and being the number of set elements in the transcript, and T is the number of transcripts that the adversary has, or the adversary sees before it performs the attack, and we're able to bound the soundness error in this way. Okay, so a couple of observations here. If we take rid of the term before P to the negative n, it's essentially the intuition that we're trying to capture before. The soundness error is just a P to the minus n. So notice that here, if we consider a protocol where the number of if we want a unbounded, which we want it to be secure against an unbounded number of transcripts. So in other words, we set T to be huge, right? If we set T to be huge, what does that mean? Is that essentially the whole thing it goes tight to P to the negative n. Okay. So think about another case where, say, the transcript or like the signature size is actually 0. Say like n is equal to 0. So it doesn't have any set elements in the transcript itself. What does that mean for us? Well, that means the P to the negative n is equal to P to the 0, which is equal to 1. Right? So how do you get a small soundness error? Well, the soundness error you can only get by setting the previous term to be small, and essentially you need to set P over the number of P, which is the number of set elements in the public key, needs to be almost as large as the number of transcripts. So in other words, you can think about it as if you don't have any set elements in the transcript or in the signature, then all of the security comes from comes from the public key, or like the hidden discrete logs in your private key. And if you want it to be secure against key transcripts, then your public key needs to be almost as large. Right? You want this P over T to be close to 1. So that's what it implies for the case where you don't set where the signature length is actually 0. Okay? Does that make sense? Right. So next up, we'll take a look at our intuition on the proof outline for our central piece that's F is equal to P to the negative.
I'm confused about the length. It's like you have this lambda squared over log lambda. That's like the public key plus the signature, or
yes, public key plus the signature. Yes. Because if you only care about signature space, you can set the signature has to be 0 and the public key can be.
Okay. So if you set the public key to be larger, you can have a very small signature.
Yes, that's correct.
What's like the drawback of having a large?
It's that each verifier needs to have access to this huge boundary. So essentially, you can think about like, for example, you can just have a lot of secret discrete logs, and each time you just reveal one. And you just essentially have public key has a lot of components, and you just get rid of one each time.
But if you use the signature scheme to sign multiple signatures, the concept of the public key distributing the public key can be done.
Yes, that's correct. but,
So I guess when you have a table where it shows like the length of the signature, does that include the public key? Like,
yeah, that includes the public key, yes.
but I guess like for many practical applications, it's not a drawback. Right? You can make the
If you have a huge public key together with small signature sets, yes.
how huge will it need to be if I want to?
It should be, if you're, yeah, as I was saying, if you want it to be secure against n, for example, you want it to be n times secure, it needs to be as large as n. So like, if you want it to reduce it n times, it needs to be as large as n. Essentially, you're just like doing n separate signature protocols.
I guess maybe I'm confused. N is the number of.
I'm sorry, yeah, t is the number of transfers, yes. So if you want it to be secure against t instances, then it needs to be as large as t.
If you want it to be, but this is when the signature is small.
Signature is small, yes.
If the signature is large, then it can be small depending on.
It has small dependence on t, yes. Exactly.
So what if I wanted to be able to sign unbounded polynomial many times? Then what's the lower bound on this? Maybe I mean, I cannot internalize all this calculation.
If you want to say, if you want, so you want to be secure against a large, an unbounded number of transfers, right? So this way t goes to
Polynomial.
a polynomial. Yeah. So this way t is large, and then you can potentially set p to be small. Yes. Now it essentially just goes to p to the negative n. And
In this case, the public key is small, but the signature will be large.
in this case, I mean, it just fulfills this bound that s is equal to p to the negative n, and you can play around with how you balance the public key and the.
Do you have like some physical parameters?
I don't think we have.
I cannot just.
I mean, the optimal one is.
calculate
I mean, the optimal one, it would be that if you add them together and you want to minimize the sum, then the optimal would be lambda squared over log lambda. That's how we arrive at this lower bound.
The optimal is like the sum of the
Yeah.
sum of the.
The sum of two. If you want to minimize that value, you get that by setting p equals n equals lambda over log lambda.
But I feel like the sum of the two is a little bit deceptive metric, right? Because it's like you're not
To lower bound the length of signature because you have the length of signature to be zero, right? So you can have the length of signature to be zero, so that we're going to find that meaningful to give a bound of zero. So that's why it's more meaningful to give a bound of the public key size plus the.
I think it's like the curve that's interesting, not just the single point, because you can argue that you know if I can make the public key slightly larger.
Yeah, and the curve is what we give here. Yes. This
Okay,
is
I guess, sure.
you should say it's a little bit hard to picture what it
Yeah,
looks like. Yes.
Like some program. This is
I see.
it's just a little hard to.
Okay.
I mean, obviously, if I spend like 15 minutes, I can internalize it.
You can draw it more deeper distance. Yes. I see. Yeah, I think so sort of like this trade-off is given by this specific result. Like the lambda squared over log lambda is the optimal result that we get, and the trade-off is described by this main theorem. Make sense?
Yeah.
Okay. Yeah, I guess I should probably maybe for future talks I'll make sure to add some the particular parameters what it means for this equation. Okay. Cool. So yeah, and then lastly, we're gonna quickly take a look at sort of the outline of the proof and sort of like how exactly do we arrive at this equation. So the idea is pretty much follows our intuition in the previous Schnorr protocols. Essentially, we show that an adversary should always be able to guess something correctly with a given probability and then repeat that many times. So what we do is we take a specific interaction between the prover and the verifier, and we look at the transcript. So first of all, there is a public key that has, say, p set elements, and we look at the transcript, the interaction between them, and their interaction. The transcript also has, say, n elements. Okay. So now, what we think about is whenever the verifier makes the query makes a query to the group action random oracle, right? It's going to give you some sort of discrete log relations. It's going to tell you, for example, A1 is equal to H star X1, right? And we sort of want to represent these discrete log relations into a graph. So we're constructing a graph from the corresponding transcript. So in this case, let's say the verifier gets that A1 is equal to H star X1. What we do is we add a edge between the set element A1 and the set element X1. And here A1 is in the transcript and X1 is in the graph. Okay. So notice that these discrete logs, because say in the second case, let's say we get another query and it tells us that A1 reveals a discrete log between A1 and A2. Okay, so now we connect A1 and A2. Okay, notice that these discrete logs are transitive. So if you know the discrete log between A1 and X1 and the discrete log between A1 and A2, you automatically know the discrete log between X1 and A2, right? So now, essentially, we can think about it as a connected component. So within a certain connected component, you know the discrete log between any two set elements that are in the same connected component. Okay. So what we do is, right, we add on the edges for each of the query that the verifier makes. And now think about what an adversary needs to do. Well, if we view the connected components and put them into different colors, essentially what an adversary needs to do, when adversary needs to produce a certain set element in the transcript, what the adversary needs to do is to guess what color it is. In other words, which set element in the public key it is connected to. If you guess correctly, then you can sample the element A1 in such a way that you know its discrete log corresponding to X1. Right? For example, if I guess incorrectly, if say I guess A1 has the color purple, and then I construct A1 sort of knowing its discrete log from X3, then I will be problematic because A1 supposedly you should know the discrete log between A1 and X1. Right? So if I'm able to guess the color correctly, then the adversary is able to perform the attack. Okay. So in this case, there are n set elements in the transcript, and you need to guess the color correctly for each one of them. And how many colors there are? Well, first of all, we assume a simpler case where all the public keys are in separate connected components and therefore different colors. Well, in this case, you have p colors, and you need to guess n times. So the result is p to the negative n, as we would mention, right? So here, guessing the color is corresponding to guessing the index in the Schnorr signature protocol that we saw before. Okay. So here are some other. So now you might be questioning like, where do the other terms comes in? Well, notice that what if there are like two public key elements that are actually connected in the same connected component? That will reduce the total number of colors, right? If X1 is connected to X2, then they should be the same color. We have one less color, right? So essentially, what we show is that if you have such two public key components that are connected together, you might as well just build another protocol with only one of these public key elements, and you just record, because you know the discrete log, you can always compute X2 from X1. So for example, in this case, then X2 could be extra. You can get rid of X2, and that leads to the term P over T. Okay. You can apply the similar reasoning to the set elements in the transcript. So the adversary could potentially the adversary needs to generate all of the edges in the graph correctly in order to convince the verifier. However, the adversary could potentially introduce other edges that were not originally there. And to get rid of those, we essentially show that if the adversary creates an edge between two set elements that are not actually in this graph, following the same reasoning about public key elements, we get this 1 over polyton. That is sort of like the result that we have. So yeah, it's a very high level description of the proof, but the central piece is essentially through this argument of connected components. And the other ways are to reduce any protocol down to this normalized protocol with connected components. Okay. So there are a couple of further extensions that we introduced in the paper. First of all, we show that we allow direct sampling of group elements. Of set elements. So instead of having a set element coming from the group action oracle, you can directly sample a set element out of nowhere. You don't need to feed in a set element to get a corresponding set element. This is actually not used by any existing group action-based signatures. So without it, our bound still makes sense. But it's sort of like supported by the literature. So we think, okay, we might be as well want to have that in case other implementation actually requires this power of directly sampling. But yeah, we show that even we allow direct sampling, our bound still holds. And the second extension that we have is what we call black box graph actions. So in the previously we are still having this group elements for the group. Those group actions are sort of still in group. Now we imagine that these actions that we take does not have a group structure. Now what we mean is essentially like a specific action is now, imagine you have a graph and the nodes of the graph are set elements, and an action is essentially a walk on that graph. So you start with the element, and then you walk several steps, and then you will end up at another set. Okay. So in other words, we can think about group action as a graph where the edge labels are group actions. So the actions follow a group structure. But those are sort of the extensions that we have. And yeah, so to sum up, so our conclusion is, okay, so we show a lower bound of lambda squared over log lambda for group action-based signatures, and we show it matches the state-of-the-art constructions. Essentially, this bound is tight. And on the other hand, how to circumvent our lower bounds? There are several ways. First of all, for example, you can construct signatures not from ID protocols, because our bound is ID protocols. If you break that assumption, you'll be able to circumvent the bound, or you make non-generic queues, or you introduce other things. Okay. Yeah, I think that's the topic today. Thank you all.